Okay, today we're going to talk about vertical stretch and vertical compression. So we've already discussed the horizontal shifts and the vertical shifts of parent functions. Now we're going to talk about the A value. So when we talk about A value, what we're talking about is, if it'll change slides, here we go. We're talking about the number right here in front of the f of x. Alright, so remember that our general formula is A f of x minus h plus k. Remember, this is horizontal. This is vertical. And the A value tells us our stretch or our compression. We're going to call it a compression because I think it makes a little bit more sense than a shrink. Stretch or compression. So you can't have both, you can have one or the other. So we need to define how we determine that. So the A value determines that based on what value it is. So if the A is greater than 1, meaning it's like 2, 4, 7, whatever, alright, we say that it's a vertical stretch. Okay, what that means is, say I had the point 0, 4. 1, 2, 3, 4. Okay, I'm going to multiply the y value by 2 to get to 8. So it's going to stretch, and it's going to get further up from the x-axis. So if I had an 8, say that was the tip of a parabola, it's going to make it a little bit stretched out. Okay, basically it gets skinnier. A vertical compression, on the other hand, say my vertex or my starting point was at 0 and 4. When I multiply it by a fraction, because when A is between 0 and 1, it's a fraction, 1/2 of 4 is 2. So what happens is my compression actually makes my graph get bigger. So compression makes it fatter and a stretch makes it skinnier. So think of Stretch Armstrong, he gets skinny as you stretch him out. Right? In a compression, you compress two things together, it flattens out between two boards. Okay, so if A is a whole number bigger than 1, or not a whole number, but a number bigger than 1, it's a stretch. If A is between 0 and 1, meaning it's a fraction number, then it is a compression. So let's look at an example of this. Alright, so say we have 2x squared. 2 is bigger than 1, so we know that this is going to be a vertical stretch. So let's look at the parent function x squared. We have a point at 0, 0. We have a point at 1, 1 and negative 1, 1. We have a point at 2, 1, 2, 3, 4 and negative 2, 4. Okay, so that's my parent function. I'm going to draw it dash just like we did in class last week. Okay. Now I want to graph a stretch function. I'm going to change my color so that you can see the stretch function. Now the table of values that we started with was, we had negative 2, 4, negative 1, 1, 0 and 0, 1, 1, and then 2 and 4. So what I'm doing is I'm multiplying each of these y values by 2. So I'm going to times each of these by 2 to get my new function. When I do that, my new y value is going to be 8, 2, still 0, 2, and 8. So I'm still going to have a point at 0, 0, but now my 1 value has stretched to 2. My negative 1 value has also stretched to 2. My 2 value, which was originally at 4, is now going to be 1, 2, 3, 4 higher because it's at 8. And this one's going to be 4 higher, which is at 8. So my stretched graph, as you can see, has gotten skinnier than the original parent function. So a stretch is skinnier. Okay, Stretch Armstrong was skinny, right? If you even know what I'm talking about. So a vertical stretch is when it's greater than 1. Alright, so let's do an example of vertical compression. So again, we have the x squared function because it's the easiest one to see this. So let's go back and change it to red because red is our parent function. Change. Maybe not. Click, click, click. It won't let me click. Click, click. Alright, well, nope. Alright, there it goes. Okay, so we have a point at 0, 0, 1, 1, negative 1, 1, 2 and 4, and negative 2 and 4. So that's my parent function. Now in this case, instead of multiplying by 2, we're multiplying by 1/2, which because it's a fraction is actually going to make our graph get smaller, our y values get smaller. So remember we have -2, -1, 0, 1, and 2, and this is 4, 1, 0, 1, and 4. Remember this table is our critical points. So now instead of multiplying by 2, I'm multiplying everything, all the y values, by 1/2. 1/2 times 1/2 times 1/2. So my new y value is half of 4 is 2. Half of 1, or 1 times 1/2, is 1/2. Anything times 0 is still 0. And then it goes the same numbers again. Okay, so these are my new y values. We'll call it y prime. So let's see if it'll let me change my colors. Change it back to blue. Alright, so now I'm going to graph the same x values but with the new y's. So I still have a point at 0, 0. Now this 1 has become 1/2. So it's going to be about right there. And same for this one. The 4 is now at 2. 2. Okay, so if you notice, these points lie underneath that graph. Well, when I sketch it in, you'll see, kind of, if I had done bigger numbers, you'd see it better, that that is a fatter graph. Okay? So a vertical compression, this is a vertical compression, it compresses the graph towards the x-axis, meaning it's going this way towards the x-axis. So think about, you put a brick on top of this graph, it's making the graph go towards this x-axis right here. Alright, so a vertical stretch makes it skinny, it stretches it this way. A vertical compression stretches it this way. Okay, so that's the a value of a function. Now, if you notice, it's an absolute value. We haven't really talked about this, I mentioned it in the last video. But we also have what's called a reflection. When you're talking about reflections, say we had f of x is equal to -x squared. Our original parabola, remember, sits like this, and I'm not going to draw my points, so don't get crazy. That's our original one. When it's a negative sign in the front, meaning this could have parentheses, what that does is it reflects it across the x-axis. Okay, so this negative sign is separate from if it's an a value. The a value, you take the absolute value of it, meaning you just take the number, and if there's a negative, you flip the whole graph. Okay, so that sums up all of our transformations for parent functions. Make sure you took good notes over this, and if you didn't, watch it again. I hope you had a good weekend.